The practical era of quantum inspired machine learning 2.0 for healthcare is beginning February 17th, 2024. Starting in 2019, an increased number of quantum inspired publications and demos were made available to the public for use. This trend continued through 2021, where iterations of medical image analyses using quantum inspired machine learning algorithms were performed in fields such as COVID-19, rheumatoid arthritis, and brain tumors. In general, the algorithms were faithfully simulated to represent exact quantum values similar to running on a quantum computer. By and large, the results using this method of converting classical images into quantum states and then back into classical information were slow and in general yielded above average results versus established classical methods. The more effective approach to utilizing classical algorithms inspired by quantum mechanics has been to implement processing methods that approximate quantum information. This is done to retain as much quantum benefit from algorithms and systems, and then convert all necessary components into classical algorithms for native use on classical computers. Several authors in 2024 across three quantum-inspired fields reduced classical RAM requirements while achieving speedups or performance improvements to create new, more scalable quantum-inspired algorithms. In other words, utilizing approximate quantum-inspired methods can now solve larger problems previously unattainable to medical researchers. The first field of quantum-inspired approximation is referred to as dequantized algorithms. Several quantum algorithms once believed to have exponential speedups running on quantum computers now resemble convenient and efficient classical algorithms within time complexities of polynomial overhead. The field led by Ewan Tang, Anish Bakshi, and others continues to narrow the quantum classical gap, resulting in new effective quantum-inspired versions for regression, recommendation systems, or Hamiltonian simulation. The second field of quantum-inspired approximation is in employing tensor networks. Tensor networks have been shown by New York University and Flatiron Institute researchers to scale to higher qubit systems without quantum noise or decoherence and offer significant improvements in accuracy and precision versus quantum computers or prior generations of tensor networks. Quantum circuits and quantum systems are estimated using efficient processing methods to accommodate for larger problems for higher performance that would normally exceed classical RAM capabilities if researchers had used state vector algorithms. The original field of quantum-inspired state vector algorithm simulation has been the primary focus for many medical researchers. Although the number of qubits has been nearly tripled to 192 by IBM Quantum and IonQ in 2024, extensive software techniques such as circuit cutting and qubit reuse would further be needed to increase the total number of available qubits. In order for loss and RAM performance to improve, approximation techniques to obtain classical algorithms without requiring quantum state preparation will be needed. Many aspects of today's traditional deep learning methods, such as training convolutional neural networks, use a variety of approximation techniques to increase efficiency to solve larger problems and have been FDA approved for safe and effective radiology use as artificial intelligence medical devices. And quantum-inspired implementation continue to use similar linear algebra techniques to further improve access to speedups or accuracy gains. Quantum-inspired machine learning using classical data in industry will continue to be the primary form of quantum computing to assist artificial intelligence for the analysis of medical data. This is due to the utilization of high fidelity and readily available CPUs, GPUs, or TPUs. Widespread and economical classical hardware availability is the key for advancing the technology's innovation through the iterative process of research by organizations across the world. The three quantum-inspired fields represented by 2024 papers will potentially be further improved in the following feasible ways. Option number one, a dequantized algorithm approximated from a quantum algorithm will be used to speed up an existing quantum-inspired regression workflow. Option number two, a larger quantum system utilizing mean field theory will be approximated accurately using a tensor network that will continue to also scale with other systems. Option number 3, a 100 qubit quantum state vector circuit will be incorporated as an exact solution using a medical machine learning workflow with advanced software techniques and higher levels of computation. In summary, all quantum-inspired machine learning 2.0 methods, also referred to as QML 2.0, mentioned here are inspired by quantum mechanics, but utilize purely classical algorithms, whether quantum states are utilized or not. References are available in the comments below. Have a productive rest of your day. Good to go.